You should find this handout from yesterday. What I'm going to do is I'm going to give you the really quick, like the 3-minute version of the Millikan experiment. Yesterday was a presentation. You missed
never mind.
0. All you missed was that handout. Yes.
It's just because you said it yesterday. So I didn't remember.
If you were away yesterday, you need this.
What?
If you were away yesterday, I did hand this out. Who was away? Did you do?
It was horrible.
Have we got the same, please? Time to go.
This is the bus right now.
You don't know her yesterday, right?
We're walking around.
Check it out. All right.
I can tell.
Okay, Jeff, put it away, man. Time to go. Class, learning, listening. Okay, so an experiment performed by Robert Millikan in 1909 determined the size of the charge on an electron. So that was the purpose. He was trying to figure out what is the charge on a single electron. And what number did he come up with? Anyone know? Anyone? Further? 1.6. Yeah, 1.6 times 10 to the minus
19.
19, exactly. He's very small. He also determined that there was a smallest unit charge, or the charge was quantized. In other words, it came in that's the smallest amount you can get. Okay? And I always use eggs as my example. When you go to co-op, you can buy a pack of 12 eggs, you can buy a pack of 6 eggs, you can buy 18 packs. I don't even know, can you buy 24s? Yeah. Okay. But they probably won't sell it to you, but the smallest amount of egg you can get is a single egg, right? Like you can't buy a half an egg, right? Wow. It's quantized.
So that's like...
That's what they mean by quantized. There is no smaller. You can't go any smaller. That's it. That's the smallest amount there is. Right?
We're making it something else.
He received the Nobel Prize for his work. Good for him. We're going to explain that experiment here, and Sean Millikan was able to determine the size of a charge on a single electron. So here's what he did, right? He put a charge, what Millikan did was to put a charge on a tiny drop of oil and measure how strong an applied electric field had to be in order to stop the oil drop from falling. Since he was able to work out the mass of the oil drop and he could calculate the force of gravity on one drop, he could then determine the electric charge that the drop must have. By varying the charge on different drops, he noticed that the charge was always a multiple of minus 1.6 times 10 to the minus 19. Now, what I mean by that is, what does multiple mean? Like, what are the multiples of 3? 6, 9, 12, right? Okay, so what they're saying is, and I'm simplifying this, Millikan discovered that the charge was always like 6, 9, 12, 15, 27, 36, 15, 18. He looked at all these numbers, probably made a graph, probably found the slope, by the way, and found that if he found these numbers, he would find that the slope was always approximately 3. Okay, now, but his number was not 3. His number was a whole lot higher. His number was 1.6 times 10 to the minus 19. So, in other words, what he found was that his charges were like 1.6 times 10 to the minus 19, and 3.2 times 10 to the minus 19, and 4.8 times 10 to the minus 19, and so on and so on. And you can imagine having to do a graph like that in 1909. It wouldn't involve a laptop. Exactly. It'd be trouble. He'd need nice graph paper and a sharp pencil. And an eraser, right, AJ? No, they would use pencils. This meant that it was electrons carrying this unit charge. So in other words, he discovered, or he proved, he showed that the smallest amount of charge was this 1.6 times 10 to the minus 19, and this C. Anyone know what the C stands for? Coulombs. That's the unit of charge. Coulombs, not coulombs, coulombs. This is what his apparatus looked like, and here's how it worked. In fact, I have one here. I know, it's crazy.
Yeah, we're going to use that as a prop.
I know.
We got to redo the whole thing. Perfect. We got to redo the whole thing.
Okay, so here is a simplified lab version of a Millikan apparatus. Now, Many years ago, when I had Harris, that back room was like a big storage room, okay? And when we decided to clean it up and we're turning into a computer lab, we hauled out a bunch of stuff. I literally found about 12 boxes of these unopened. They've never been used. Yeah. So this was in June. I spent an afternoon trying to get one working. I couldn't get it to work. I couldn't figure it out. The instructions were kind of hard to understand. So we tossed a bunch, but I kept one just for display purposes. And it's kind of getting beaten up a little bit. But this thing, which I will pass around, you can see, you hold it up to the light, and you can see on it's like a microscope, and it's got like little markings. And it goes like 8, 7, 6, 5. So they would use this as a way to sort of figure out how fast that oil droplet is falling.
So you still think it's
Ready? No, I've never tried. Or I did once.
Can we pass that around?
I will pass it out. I'm going to show how it works. So this would go right here. This is the light source. It's just a really old flashlight. Sarah, you should watch. Okay. There's a light source here. This little container right here is, instead of using oil, they use little graphite, little teeny tiny, incredibly small little plastic balls. They were all dried out, and that's what really didn't work. And then there was, at one point, there was like a rubber bulb that just squeezed and it would shoot them through the tube. And you can hear it. This part right here, this is the chamber. And I'll send it around. You can see there's two sort of flat plates, I guess you'd say. They're both a little less than a centimeter apart. And then this thing you would look through and you would see the oil droplets falling. Okay? And then there was, this would hook up to a battery and you could adjust how much electric fuel it was. Okay, so it's kind of cool. I'll send that around. So what Millikan did was, on his device here, the atomizer, which is really just a fancy word for a spray bottle, would spray oil droplets into this area here. Can you see the little oil droplets in there?
Yeah.
Okay, so there's all these little oil droplets in here, and then right here there's a hole in the plate, and so some of these oil droplets would fall down here. Okay? Now, this plate and this plate were charged. Here's the battery over here. Okay? So you've got these oil droplets in here. Here's the microscope where you can see them. So what would happen as the oil droplets fell in here? Well, they would simply do what? They would fall. Zane, you should put that away and listen. I'm explaining things. So the oil droplets would fall in there, and then he would turn the electric charge on. Now, because the oil droplets were charged, some reports say he used X-rays. Some reports say that just the friction would do it, but they were charged. And then once they were in here, if they had a negative charge, what would force them up? Which one would be positive, Brett? The top or the bottom? If the top was positive? Okay, so if the top was positive, that would do what to the negative charge oil droplet? It would attract it, right? And then if that's positive, then down here you would have, not other way. Right, down here you would have negative charge. And so the electric field would be taking that oil droplet and pushing it up. Now what if, do I have it here? What if, that's what this is all about. I'm just going to explain, I'm not going to bother reading it. What if the weight force due to gravity down was the same as the electric force up? It should hover. Right? You should be able to adjust the electric field, and you might have tried this with the simulator. You should be able to adjust it so that those forces are balanced, which means that the net force is 0. Now, Fw is equal to mg, right? So what he did was he used some fancy math, and I'm going to show you kind of a simulation of that. He did some fancy math to figure out the mass, multiplied by the gravity, he got the weight force, and then he said, well, that's equal to Fe. And using that, he could figure out what the charge, which is the letter Q, is on it, okay? So that's kind of how the Millikan thing worked, okay? And that's what they're talking about here on this page. It turns out that the formula for electric force, Fe, is Q times E. The force, the electric force, is Q times E. And you're going to get this in notes right away, where Q is the charge, and E is the electric field strength. And to increase the electric field strength, all he did was give more battery power here. That's what increased the electric field. Yeah, basically, yeah. Okay, and then he could figure out what the Q was. So blah, 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 blah. He obtained various values for Q. Now, the charge Q on a dot was always a multiple of 1.6 times 10 to the 19. So he declared that number is the charge on a single electron. Now, I think he actually came up with 1.59 or something, right? Yeah, it's a little bit sort of slightly off of that. And modern scientists have done it, and they get something that's pretty close. Okay. Now, do you remember, what did it say about the controversy? There was two of them. What was the controversy? Anyone know?
Who was the first to discover the...
What's that? He excluded some data. He said, I'm not going to count that because why, Hayden?
It was only for drops that were like completely tested or whatever.
Something, yeah. He basically said, I'm going to ignore those. The problem is that many people believe that he had that number in mind. It was kind of like a race. There was Millikan and there was this other guy, and they were both trying to come up with this magic number. Millikan had his ideas, the other guy had his ideas, and it was kind of a race. So a lot of people believe that Millikan had his number and then went and looked for data that matched it. And the ones that didn't, he threw away. Okay? Is that good science?
No.
It's not really good science. A good scientist actually has his idea and then looks for things that disprove it. Okay? It's called confirmational bias. I can't remember what this one is. True. Okay, so what is an electric field? Actually, a lightning strike like that really doesn't have a whole lot to do with electric field. It's just a cool picture to show, and it's a way for me to identify what notes I'm talking about. Cole, you should really put that away and really, really, really focus, okay? Because I can see that it's really distracting for you today.
Did you know
Okay.
that lightning bolts at the same time?
You're going to miss the girl now.
Exactly. That's
Okay, let's put Zane on there too so you don't feel bad.
I don't know.
Okay? It'll be fine. Oh, you can do that. Oh, yeah. Okay. Good idea. Fair enough. Fair enough. I'll make it voluntary, but I do appreciate it. Thank you.
It was voluntary.
Well, not for you.
Here, Mike.
You're a good D for the day. Oh, it's just buzzing away here. Just as a show of solidarity.
Probably just a fake phone.
Yeah. Keep it faithful just for that. Ah, Johnny. Okay. So, an electric field is actually very similar to a gravitational field. A gravitational field, and I'm going to show you the similarities. A gravitational field is defined as the amount of force exerted upon a unit of mass, or 9.8 newtons per kilogram. More than once, you saw me jump on the scale, and for every kilogram of mass that I have, it shows 9.8 newtons. Okay? So 9.8 newtons per kilogram. How does that now relate to an electric field? Okay? As well, gravitational field exists around any object with mass. I have a gravitational field. Cole has a gravitational field. Brett has a gravitational field. Everyone in the room has their own gravitational field. Those of us that are larger have bigger gravitational fields. No big deal. Large masses, such as planets, have a strong gravitational field. Right? The planet is the biggest thing in our neighborhood with the biggest gravitational field. Okay, so that's kind of review. You probably don't need to write any of that down. Now, around charged objects, there exists what's called an electric field. That has to be a charged object. Can I highlight that? I can't. Around any charged object, there exists an electric field. Objects with a large charge, just like objects with a large mass, objects with a large charge have a strong electric field. These fields are shown by a series of arrows radiating either inwards or outwards, and these are lines of force or field lines, just like gravity. What did gravitational fields look like? Remember me drawing this? They look like that, right? And if it's a bigger object, the lines are simply what?
Closer together.
Closer together. Zane is correct. closer together. Right? Do they always point towards Zane? Not towards Zane, but Zane, do they always point towards the object?
Yes.
How come? Gravity always pulls? It always pulls in, gravity never pushes. Gravity never pushes. It would be weird,
Floating all of a sudden.
right? What do you think about electric fields? And I've kind of already given you the answer to this already today.
It's like pulling.
They're the same thing.
They're the same thing, they only pull,
How they break the.
they can push,
They can say
the same charge.
It doesn't really push, it just travels.
Okay, what do you mean?
Wait, what?
Like the electric field you're talking about, it doesn't really push, like it kind of just moves around.
Okay, so what if, and I can't really do it easily,
It's like-
what if you do the old balloon trick on your head,
That's what
right?
I mean, then you go and touch something, you're not like pushing the electric to the carpet or to
True.
the person, you're not like zapping it to pull, it's like.
Okay. I will try to get the
Balloon.
battery generator going next week. But if I were to put a charge on, say, the balloon, right? And then I've got maybe like some Kleenex, and it has the same charge, what would happen? Would it not push the Kleenex away? So does it not push then? Like if things have the same charge, it would push, right?
Ruler thing,
What's that?
hair. The ruler thing with their hair.
The ruler thing.
Yeah. Oh my god, I gotta show you this.
Is this another one of those Brazilian black magic kind of thing?
Oh wait, never mind. I can do it with,
One man.
Can you do it with my hair?
yeah.
This is going to be cool. Okay. Here is an electric field. You will notice.
The arrows are going the opposite way.
Yeah.
Positive, look at it.
Note that the closer the lines are to start the field, there's something missing here. Hang on. Something missing here. Okay, well, notice that it is positive. Now, can things like planets, they have a mass, right? Does antimatter exist? And it does. It's kind of mind-blowing, but antimatter does exist. But matter, there's only one sort of, like it's just, it has mass or it doesn't, right? So that's why it's pulling. Whereas a charge can be positive or negative. There can be two states, two possibilities. So positive ones, actually the electric field goes away, and negative ones, the field actually goes
Zapping gravity.
towards. No, it does not mean gravity stays.
Well, we use it as a negative.
Yeah. Now, a lot of this is a convention, and I'll explain right away. But I should point out again, the closer the lines are, the stronger the field, and this strength is dependent upon the distance. And once again, the inverse square law applies here. And what is that inverse square law? And this was on the test, by the way. Twice as far, 1/2 or 1/4? 1/4 the strength. If it's 3 times as far, it's 1/9. If it's 4 times as far, it's 1/16. Same thing with electric field. The farther you are away, the less it is, right? The same thing with sound. If you're at a rock concert and you're right beside the speaker, it's crazy loud. As you get farther away, it gets softer. Inverse square law. Okay? Inverse square law. Light is another one. Magnetism is another. All follow the inverse square law because they're kind of circular. Blah, blah. Let me just make sure. Yeah, okay. Okay. This is the most important part. To show the direction of the field, bring another smaller charge, a positive test charge. It must be a positive test charge, and it will be repelled. So if this is a positive big charge thing, and you bring in a little teeny tiny positive test charge just to test it, it will be pushed away. How come? Positive, they repel. How come we don't use a negative test charge, Mr. Bennett? So you say, how come we don't use a negative test charge, Mr. Bennett? Oh, that's a good question. They just said, you know what? It has to be one or the other. Let's use positive. And then everyone shook hands and agreed.
Yeah,
You guys didn't have a say in the matter. Tough luck.
so if I could get this
Because people want to know. Why does red mean stop? Did you guys have a choice in that matter? No, it happened a long time before you were born. Some things you don't get a choice. Red means stop, positive test charge. Those are the two things in life.
The only two things.
Those are the only two things in life you don't get a choice about. Positive test charge.
Right on.
Objects with a positive charge have fields that point away.
Actually.
Positive charge points away. Okay? If you were to add a large negative object, what would happen to the positive test charge? Well, it would be attractive.
Real quick.
So, objects with a negative charge have fields that point towards. That is really the big idea here. Okay? Is that an easy question to get right on a test?
Yeah.
Is it also easy to get mixed up and get it wrong?
Yeah.
And is there anything in between part marks? No. You will have to draw many different fields. There's about 8 of them on the test. If you screw them up and you always put negative away, guess what? 0 out of 8.
Woo.
Don't do that. That would be stupid. Get it right. Put it on your cheat sheet. I noticed some people didn't have cheat sheets attached to their test, by the way.
Yeah.
I'm hoping it's because you just didn't attach it.
Well, I just.
Oh, are we supposed to?
Yeah. I just wanted to see it, that's all.
Oh, I didn't.
Junior, get the earbud out. Objects with a negative charge have fields that point toward them. I'm winding down here. Okay, now, this amount of attraction, how much force, this amount of attraction or repulsion can be used to indicate how strong the electric field is. Because the stronger the field, can I go back here? If this is stronger, then how much force is going to be on this guy? More! Right? The more force, the more field strength. The more field strength, the more force, and so on. Okay? The field strength is defined as the force the field exists on a unit of charge. Now what is, when we talk about gravitational field, it's newtons per kilogram, and the unit of mass is the kilogram. What's the unit of charge? What's the unit of charge?
Yes.
It starts with a C. Coulombs. The unit of charge is the coulomb.
I got some wrong with class.
E, electric field strength, here's your formula. E, electric field strength is the electric force over Q, the charge. That one you should write down. If you're not writing anything down, write that one down. Well, it's up to you, man. Some students write notes down.
Yeah, I just grabbed it.
E equals F over Q. What does E stand for?
That electronic thing.
Electrionic, yes. Electrionic. Kafufe.
That's what electronic.
E is the field intensity or strength, and it's measured in newtons per coulomb.
Hey, we are. What's FE?
Fe stands for the force. What kind of force? Electrionic.
Electronic.
Electric force.
English is not a good language for me.
Kafufi. Electric. What does Q stand for? Exactly. Charge. Measured in coulombs. Coulombs. Kind of a fun word to say.
Johnny, you should hear Johnny.
Should hear Johnny say coulomb.
Columns.
Yeah, he literally pronounces columns, and I'm like, Johnny, we have to do the whole thing again. No.
Columns. Well, maybe I got it wrong. I don't know.
No, it's definitely cool.
Charles Coulomb, I believe, is who it's named after. Okay, so you got, because F is measured in newtons and Q is measured in coulombs, electric field strength is newtons per coulomb. It's similar to 9.8 newtons per kilogram. Now on Earth, I should say, on Earth the number is 9.8, right? But every charge has its own number, right? Like bigger charges are going to have bigger numbers, right? If it's a bigger planet like Jupiter, it's going to be more than 9.8. Smaller planets like the Moon, smaller number, 1.6. Right, 1.6.
Remember that they want
Now, here's a question that I often get asked. The intensity or strength of an electric field is the same for a positive charge as it is for negative. Only the direction is different. Oh boy, do you think I'm going to ask that question on the test?
Yeah.
Only the direction is different.
That's only
Positive fields,
They got the same charge.
yeah, exactly. Positive fields have the same, or can have the same strength as negative fields. It's only the direction that's different.
But they have got the same charge.
They have to have the same charge, yes. If they each had, say, 10 coulombs, field strength is the same. Equal.
Different.
Just wait, I want to write.
I have the drum now.
Yes, okay. Here's example number 1. You should write this down. You will have to be able to do problems like this, Jeff, on the test. I am showing you how to do problems like this right now. I know it's crazy. I've never done it before where I show you how to do problems.
That's impressive.
Well, that's why everyone's been having such a hard time.
Exactly. I should have done more sample problems.
Yeah, you
Austin.
should have.
Yeah. I don't know what I was thinking.
Do we get our test back by chance?
Yeah. Yeah, I finished it off yesterday when you guys with that thing.
I think it'll make it easier if someone said, can I have help? And you did it, so.
Oh, you got the answers.
That's what he said.
What?
Answers. And you just-
I encourage you to find the help on your own first. If you're still having trouble, I'm glad to help you. What I don't do is individually tutor.
I'm giving
Yeah, that
you,
costs actually, it's more charge.
I'm giving you the two.
I tutor as a group, exactly. All right, so here, what is the electric field intensity at a point
Wait.
where positive
Oh boy.
Wait.
It must be Friday.
Gee, do you think?
Oh, this one. Oh, right on.
It reminds me, I haven't done a
Now
test.
we can go. No, wait.
Wait for it.
All right.
What are you doing?
Wait for it.
Yeah. All right.
It's gonna be legendary.
I'm gonna listen. You're gonna be led. Wait for it.
Okay, what is the electric field intensity at a point where a positive charge of 2.4 times 10 to the minus 6 coulombs experiences a 3.2 Newton force? Now, sometimes, I realized this when I was doing some marking yesterday. I realized that students don't understand what the numbers mean. And then I started thinking about why don't they? And it's because of units. So you need to start getting better, because I always put the units in there, right? What is the electric field intensity? So that is solving for E at a point where a positive charge, 2.4 times 10 to the minus 6 coulombs, that's the Q, experiences a 3.2 Newton force. That is the F. Q stands for charge.
Why do you want F-E on the
It should really be FE, yeah. Electric force.
feet?
Okay, so we're gonna use this new formula that we have, and we're gonna say E equals, the FE is 3.2, and the Q is 2.4 times 10 to the minus 6. Now, have I talked about scientific notation yet?
Yeah, that's it.
Have I talked about scientific notation?
You have
Okay. I know that my plans include a lesson on just scientific notation, but I guess we're going to have to do that now. I couldn't remember if I did it this year or not. I'll pause for a second and let you get it down and I'll explain. First of all, what do I mean by 2.4 times 10 to the minus 6? Okay, what that means is when you've got a really, really, really big or really, really, really small number, you use this scientific notation. Times 10 to the minus 6 means that it's a small number, okay? And so the decimal place goes times 10 to the minus 6. It's going to go 1, 2, 3, 4, 5, 6 decimal places over. Yes, Lane, what can I do for you? Yeah, right over there. So 2.4 times 10 to the minus 6, Jeff and Ben, I'm doing the teaching here. Here's where you get help. It's like me helping you before you even know you need it. Think of it that way.
So it's 0.0.
0.0000024. Right?
And that goes in.
1, 2, 3, 4, 5, 6. Now, Cole, you always put, this is a rule, you always go until there's one number just before the decimal place. So the number is always going to be between, say, 0 and 9.9, I guess. Right? There's always one digit there in front. So it's just a way of writing really big and really small numbers. Now, times 10 to the minus 6 isn't that small. Okay, but that's what it means. Now, fortunately, you just need to know how to do it on your calculator. So, get out your trusty scientific calculator. Yes, and a bunch of you are going to say, but I only have it on my phone just a minute. To which I'm going to say, this is physics, get a calculator.
No. 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 Leo. No. Yeah. That's not letting you.
No wonder you catch my iPhone 7. No, you're so mad.
Okay, so here's what to do. Now, some people are taught incorrectly. I feel bad. Here's how you do it. On your calculator, there should be a button that either says EXP or EE, or some of them, very few, some of them actually have a times 10 to the X. But most will have one of these. Sometimes you have to go second function to get there.
And just the X.
Right? Yeah. Not E. Don't do E. No, not EX. No. Okay. So, to do this, here's what you do. Okay? Get your calculator, put it in your hand, finger. You're going to go 3.2 divided by, don't go ahead, divided by 2.4. Do not go times 10. Don't do that. Do not do that. Go 3.2 divided by 2.4, and then you go EXP.
Oh, got that.
Then you go EXP or EE. And yes, you do have it.
Wait.
Okay? The EE or the EXP stands for times 10 to the power of. And then you go -6. Sometimes some people go 6 negative, some people go -6.
Can you 10x?
Then you go equals.
Does EX work?
No. Then you go equals, and you should get that number.
No, it's just.
What I normally do is I come around server on the road.
Then EE or
Yeah, you have 10 to.
Oh, I got EE. Cool. EE. That's all I gotta do.
Yep.
EE. I got 0.005.
I have.
Say EE and then -6.
It doesn't have to be 6 or something.
What happened? This doesn't happen after? Yeah. How'd you get there? Your calculator sucks. Shut up! You're gonna have to go literally, you're gonna have to go times 10. Next to the one.
Your neighbor's
Yep, that's it. Now, many of you will get, hang on here, many of you will get 1, 3, 3, 3, how many threes there's in?
1, 2, 3, 4, 5, 6.
6?
This is the power of the
Okay, many of you will get that number. Now, I can show you how to turn your calculator into scientific mode so it automatically does that. If you don't want to do that, you simply have to go count 1, 2, 3, 4, 5, 6, and then that's going to be 1.3 times 10 to the positive 6, because it's bigger than 1.
Yeah.
Okay? If it's less than 1, it's negative. If it's greater than 1, it's positive. Exactly. Yes, Judy. Yeah, I'll come around. Actually, what I'm going to do is I'm going to do the next sample because I'm keeping an eye on the time, and then when I give you time at the end, if I have to, I'll swing by the individuals. Okay? Just so I get the next one covered too. Okay? So I understand sounding notation is something kind of new to you. I'll keep that in mind as we're going forward here. Okay. How about you guys try example number 2? There's the question. It's the last one. Try that question. Give it a whirl. Try it in your calculator. I'll wait about 4 minutes and then I'll give you the answer. And then if you're still having difficulty, then I'll come around and deal with people individually. I'll do the pre-help. That's why I gotta start teaching, talking about these things. Instead of lessons, it's pre-help. So the question is, we need about 2 more minutes here. An object of charge 1.0 times 10 to the minus 6 is an electric field strength of 2 times 10 to the 4 newtons per coulomb, Johnny. What force is applied to the object? What am I solving for? I'm solving for F. Object of charge. This is my Q. In an electric field of 2 times 10 to the 4 newtons per coulomb. That is my E. So write the formula. E equals F over Q. The E value, 2 times 10 to the 4. The F is on top. The Q is 1.0 times 10 to the minus 6. So you're going to multiply both sides by 1.0 times 10 to the minus 6. And you should end up with 0.02. And if you want that in scientific notation, that would be 2.0 times 10 to the minus 2. The sort of the convention is, if it's more than, like once you get to minus 3, you should write it in scientific notation. People can look at 0.02 and they can see how many zeros that is, right? Yeah. Once you get past 2 or 3, then you sort of go into scientific notation. That's kind of the rule. I'm just showing all the work there's in, that's all. What really makes it hard is just the weird numbers. Right? That's all that really makes it hard. Let me hand these out and then I'll write it out. Oh, I'm done now. Okay, so there's a few practice questions. The first couple are pretty easy. That's picture me. That's the second finger lights on. There's the questions. There's the answers. There's the solutions. If you need a QR code, if you need help with your calculator, I'll come around right now and give you that assistance.